My talk today is really about about innovation, and many of us have contributed many ideas, and I've picked on 4 ideas which I contributed. I would say I probably initiated because they became much bigger in reality, and so I want to talk a little bit about that. But before that, I wanted to congratulate, I know University of Hyderabad has had activities in computer science for the last 30 years. I probably have been here for about 25 years ago when it first started, and I know we have a very good reputation in this area, and probably it's right and fitful that we now computer science, and I think it's part of mathematics before. Math, of course, is a very important department, so I think it's good that we now separating the 2 departments, and I'm happy to be part of the inauguration of the center. So my first slide is about the smartphone, just to give you a set of context of computer science. Many years ago, in most computer science departments were either born out of, were attached to the math department like you had it here, or were perhaps attached to the EE department. I think in Stanford, I think it was really originally part of EE. And, but today, if we look at computing and computer science sort of really taking over everything. And perhaps today, a new university would probably form computer science as the first department and perhaps grow EE out of it. And the smartphone is a kind of example of that. All of you, many of you have these phones in your pocket. It's essentially a very large computer. It probably has about at least a dozen processors. Some of them are running, clocking at very high rate, 200 megahertz, 400 megahertz. And what it is fundamentally it has antennas to talk to pick up, transmit or receive RF radiation across multiple technologies, 2G, 3G, perhaps even 4G, wireless, Bluetooth, Wi-Fi, NFC, near field communications. And then it has other transducers, like it has multiple microphones, it has speakers, perhaps multiple speakers. And of course, it also drives displays for presentation media, and it also has haptics by which you can, it can pick up strokes of your palm or of your fingers, and then understand, take inputs from your fingers. So it's really a bunch of transducers with a large computing engine inside it. And the amount of computing in a phone like this today probably would equal the computing of a large enterprise 20 years ago. So it's really incredible that we can do all this in a phone. So a number of the technologies involved here in the phone are from signal processing, signal transmission and reception, image processing, voice processing, lots of compression, decompression ideas, security. So a huge number of technologies, all largely implemented either by by general purpose computers or special purpose computers. And people who build phones are, in some sense, largely computer architects, people who have computer architecture understanding of algorithms, and understanding of voice processing and image processing and so on and so forth. Many of these things I'm sure you do at this institute. So with this, a phone like this has a number of ideas inside it, and many of us have contributed ideas which actually gone into practice. And some of those people are here sitting in this audience, and I want to talk about 4 of my ideas, which not all of them have got into phones, I think at least 3 of them have got into phones. Okay. So I'm going to start with my 4 ideas I'm going to talk about is estimation of Markov processes and noise, which actually was my PhD thesis at IIT Delhi. The second one will be on an algorithm called ESPRIT, which is estimation signal parameters using rotational invariance technique. The third one is MIMO, and then the 4th one is called MIMO-OFDMA, which is the underlying technology of 4G. And I'll talk a little bit about the lessons that one can draw from how these ideas came and how they evolved, and say a little bit about innovation in the Indian scenario. Next slide. So the idea of estimation of signals and noise has a long history, and the basic idea is that you have an observation which has got a signal of interest. It could be in a direction of an aircraft, or it could be anything. It could be a voice signal, which is corrupted by noise, additive noise. And the first person to look at this problem was really Carl Gauss, Carl Friedrich Gauss, a real genius, who developed method of least squares. And this is back in, I think around 1800, late 18th century, 1790. People were based on Kepler's work, the people felt there must be a planet between Mars and Jupiter because of this Kepler's idea of this perfect solids. But actually, that theory was wrong. But nevertheless, people were looking for it, and an astronomer called Piazzi discovered there was a small planet, minor planet. We don't call it planet anymore. We just call it an asteroid, which is named Ceres. And he tracked it down a little bit, made some measurements on it, and then it disappeared behind the sun, so we couldn't see it. So Carl Gauss took some of the measurements, and using method of least squares, method of fitting, he was able to predict when the planet reappeared behind the sun. So that's the first time the idea of when you have some signal of interest and noise, how do you minimize the effect of noise or maximize or get the best estimate of signal, was actually done by Carl Gauss, because he was a real genius. And then it took 140 years when Norbert Wiener, another genius, who working at MIT, was involved with design of fire control systems and radar tracking systems. And he came up with the theory of extracting signals from noise. The signals were modeled as stationary signals. That means the statistics were not changing, called stationary. And he described the signals in terms of covariance functions. And so that was well known, and many of you who learn estimation theory will certainly learn about Wiener's work. And took another 15 years, maybe more than 20 years, when Rudy Kalman and Bucy came up with the dynamical models of signal. That means you had a differential equation modeling the signal, the evolvement of signal. And if it's a Gaussian system, it turns out that the mean and the variance were sufficient. And the Kalman filter actually propagates, runs an equation for the mean of the signal and for the variance with the Riccardi equation. And so that became the mainstay of all signal processing, all estimation theory, and we still use it very heavily in everything we do. There are lots of Kalman filters running inside these phones. Then I actually joined IIT Delhi in 1969, and a few months later I switched to a PhD program, and I was there for only 2 years. I have only 2 years of leave from the Navy. But Professor Tom Kailath came visiting and gave some beautiful lectures on estimation theory. And he had a student working on the next problem of dynamical signal models of non-Gaussian signals, of Markov but non-Gaussian. And that required new tools, and it turned out that those are the pictures, Kalman is the third picture, that some work has been done by somebody called Kolgomarov in Russia, a very famous mathematician. I wasn't aware of that work, and so that got me started in the area of this problem. Next slide. So this is the basic problem. You have an observation starting at time r and running up to time s, which contains signal plus additive noise. And you're interested in estimating the value of the signal at time t, which could be at same point at s, that is the current observation point, or it could be ahead of it, could be behind it, and so on and so forth. And the Kalman filter, which we all use, uses a state space model, and then it sort of runs the Riccardi equation for the error variance. So that's the problem set up. So when I started looking at this problem, I was just come off from a ship from INS Betwa, and we had this fire control system for firing a gun. This is actually a picture of an American system, but there was a British equivalent called FPS-5, which I had worked on. And that system and understanding of how this system actually sort of ran a very minimal version of Kalman filter, but when systems were built, Kalman filtering was not known, but there are some very minimal versions. So I had an understanding of how this thing functioned. So I was holding this in my mind when I started working on this problem. Next slide. So it turns out that at that time there was some work run in Russia called Lipster and Shiriev, and there were few results about estimation of such signals of this problem. And there are many problems I'll talk about which could be solved, and there were few results. But I started working on this, and it turned out the way to model this correctly was using, you have to use a different kind of calculus, not the normal Newtonian calculus we use, called stochastic calculus. Some of you might work in it. And I was using the Ito stochastic calculus. And then so it turned out that it needed lots of theoretical R&Ds and all that. And this was actually the fundamental result, which needs a lot of mathematical understanding to understand. Even I think I've forgotten what it meant. But it is a diffusion type equation which predicted the evolution of the density function of the signal based on underlying model. And no, go back. And it turned out from this you could derive a number of results. Of course, you can derive the Kalman filter if you make it linear, and then all the Kalman filter results would come out. And I published this actually only in one paper in the Information Theory Conference, which was held actually in Israel at that time. And then I got busy we had a war with Pakistan, and I got busy with the Sona project, and never really published it further. But this had reached, my thesis reached Stanford, and there I think it was well appreciated, and Berkeley, Professor Vijin Wong looked at it. So they wanted me to come back and give a set of lectures in Stanford on this idea. But I think we in the United States were not in good terms, so the government didn't give me permission to go. This was back in 1972, I think, or 73. Next slide. So actually, this particular result cracked the problem open in a very big way, because if you look at R, S, and T, if T is equal to S and is moving forward, it's called the filtering problem, which we generally solve. If T is ahead of S, it's called fixed lead prediction, and or if R and S are fixed, and then it's called fixed interval smoothing. Lots of problems. But where I found, and these results were very few were known for the nonlinear model. But my theory actually cracked the problem open. You can get all the results. But even more importantly, it allowed a dynamical relation between R, S, and T. For example, R could move backwards, or R and S could move at different speeds. T can move faster than S, and whatever you have, along with it was differentially related, you can actually get the relationship. So you can deal with interrupted measurements, uncertain measurements. So it really was a wonderfully general theory. But somehow I never published much. I only published one paper, and I sort of lost interest in it. And but my thesis was circulated within Stanford and Berkeley, and it had a little bit of traction. Next slide. So it turns out that except for within engineering, nobody really knew of my work, and it kind of died out actually. And also the problem we took calculus was it's esoteric stuff. D by dx of x squared is not 2x; it's something else. And so the engineering community actually didn't follow up those methods, those approach, but the financial modeling people actually use it. So it turns out by 1990 or so, people had discovered my work, and it actually has been used in financial modeling of stocks and derivative modeling in Wall Street and all that. So it actually became a tool in financial analysis, not so much in engineering. So that was my first talk I want to talk about. Next slide. Next one is called estimation of signal parameters. It's a ESPRIT, rather a mouthful. Let me talk about it. Next slide. So the problem is the problem of direction of variable estimation. So if you have a radio signal coming in, or maybe an acoustic signal, and you want to find out the direction of that signal, only one signal coming in, it is a problem. I think actually Marconi looked at it in the early 1905, 1906. The idea was to have a loop antenna, which would then, if the loop faces directs magnetic field, faces the direction of the signal, you get maximum signal. When you move away, you get the minimum signal. So loop antenna kind of ideas were used, and there were loop, Adcock, Wallenberger. Wallenberger is still antennas you see in airports with a large circular array, called Wallenberger and Sweeney. So they were all single source methods, and were also very heavily used in both military and non-military applications. I think this picture is about 1925 or 30. I think people used to, nowadays spectrum is, Dr. Sarma is here, but back in 1920s, spectrum was free for all. People are using spectrum without license. So the idea was to track down these violators and so on and so forth. Go back. So around 1964, people started looking at the other problem of multiple signals. So you have an antenna array, or whatever you have, some sensor, you have many signals coming at it. What are the directions of arrival? It turned out that was a much more difficult problem. And there was a method called maximum likelihood. It's easy to formulate, but very hard to solve. So it was impossibly hard to solve. So it was really a theoretical idea, which is not too, it didn't have much traction. But then there were many ideas, Capon method, Berg method, and so on and so forth. There were probably many tens, if not tens of theses trying to understand this problem. Till 1980, just before I came to Stanford, there was a wonderful new idea by a person called Ralph Schmidt, who came up with what called music. And then, and I was working there on some of those ideas. Professor Reddy, who's here, actually joined me for some time. And then just before I left Stanford, I proposed a new idea called ESPRIT, which actually was quite a revolution, and I'll explain that. Next slide. So the music algorithm was as follows. It needs a little bit of mathematics. So it sort of says that you have an antenna array and you have a signal arriving at, it induces a complex vector of m dimensions, where m antennas, and as the signal is rotated 0 to 2 pi, you have a manifold, 1D manifold. Some of you in physics or in mathematics will understand what it is. It's just like a rope, but in hyperspace. And then when the signals arrive, you can actually make some measurement of signals, and you can extract what's called subspace of the signals, which is subspace is an object in m-dimensional space, but it is sub of that, not the entire space. And Ralph Schmidt, who actually proposed the algorithm, next slide, was a really wonderful, remarkably, he was an engineer working in industry, but did his thesis at Stanford, had this idea, and the intersection of the manifold and the subspace were the results that you're looking for. And you can plot a spectrum that comes out of this intersection, and the peaks of the spectrum were kind of the direction of arrival. So it was not the maximum likelihood method, so doesn't meet the Kramer-Rao bound. Professor Rao is not here, but his former director is sitting here. But Professor Rao is very well known for a bound called the Kramer-Rao bound. And it sort of says what is the fundamental limit of estimation of parameters. And this one didn't reach that Kramer-Rao bound, but it was much, much better than earlier methods. I wrote a lot of papers expanding it in many ways, and Professor Reddy was involved with these things, and so on and so forth. Next slide. So then, just for the end of my stay, I was actually looking at this problem, and this goes back to before I went to Stanford in 1983. I had spent 6 years building the APSO sonar. APSO sonar is sonar that was really a world-class sonar that we built in NPOL in Cochin, the DRDO lab. I headed that project, and that sonar, we were doing that. We were doing a lot of experimentation to define the system, and that sonar now is in production the last 30 years, and it's a mainstay of the Indian Navy. And at that time, I was looking at we have a signal arriving from some direction. One way of looking at what the direction of signal is to point a beam and look for the maximum of the beam. And it turns out that's the maximum likelihood, the best method of doing it. But sometime more attractive to me that time was to have a null system. We have two half beams and you subtract one from each other. Then when you go on the both sides of the signal, you get a sharp null. It seemed null was attractive because you seem to get a sharp response in the direction. Actually, it wasn't maximum likelihood, and so on and so forth. Anyway, I was keeping that in mind, and we never used null, we actually used the beamforming method in APSO. But when it comes to multiple signals, if forming one null you don't get a minimum of power because the other signals are coming in. So null forming was not the method of estimating directions. And I was keeping this in my mind for many months, trying to see how one can do this for multiple signals, till one day it cracked open, and we came across an algorithm called ESPRIT algorithm. It stands for Estimation of Signal Parameter Rotational Invariance Technique. And it turned out we had solved that particular equation. You get two EXX, EXY are covariants and cross variants of these two made to two subarrays, which are identical but unknown, and then T is some random matrix, and phi is a diagonal operator, which actually is the angle of arrival. And this was a big revolution. I think everybody would always ask me, how did you get this idea? Because for a long history of direction finding of 50 years, all uses a spectrum method. So this is the first time it cracked the problem open in a different way. And actually, this is maximum likelihood for the problem it solved. So it was a big revolution, actually. And I remember, I think I came back to US India to 1986. And I went back for a conference in, I think, in Toronto in 1990, and there were 7 parallel sessions on ESPRIT. So there were full conferences on ESPRIT. became, I think there were at least 50 PhD theses. Some of them must be in India. Professor Reddy, Professor Hari, many of them have worked on it here. And there were at least 1,200 papers across global publications. Became a huge thing. And it was interestingly, go back. It was interestingly immediately embraced. I published the first paper in 1985. I was along with Professor Kailath and a student called Richard Roy. And within a few months, it just took off, like wildfire, and became, because for one thing, it's efficient, meaning it was a good estimator, but more importantly, it was a very new way of looking at the problem, a fundamentally new way. And Professor C.R. Rao himself, who's not here, actually worked on the problem. So many famous statisticians, mathematicians worked on it, and it spawned lots of different things because it had this element of novelty in it. Next slide. So one of the areas that's really been useful is system identification. So if you have a linear system, we give it an impulse, you have the impulse response, and you want to try and identify the pole zero transfer function of the system, you can use ESPRIT to do that. By you do time samples and you can solve the ESPRIT problem. And it turns out, so that's where it's been heavily used, but also in many other applications. Next slide. So some of the areas, of course, is radio DF, which is originally where I sort of proposed the idea, acoustic direction finding, radio direction finding. System ID has been a lot of applications. Recently, I was writing a proposal for somebody's nomination IEEE, and I find that it's also been used in biology and so on and so forth. But system ID really is a big application. And in fact, the Mars Explorer, Curiosity, which landed on the Mars, I think a few months ago, actually uses some version of ESPRIT in system ID of the linkages of the robot mechanisms. And then it's also used in MIMO wireless channel ID. In fact, some of the chips that I've built, we actually use ESPRIT not for direction arrival, but we actually have a sparse model of the multipath model. We assume the signal only arrives at certain discrete multipaths. Finding the angle, the time of arrival you can do with ESPRIT, and in spectrum analysis and all that. So it's got a lot of applications. I said many theses, thousands of maybe more than 1,000 papers. And many applications, many of them are classified, so I don't know what I think many of I'm sure US Defense is using it. I don't know much about it, but there's some interesting unclassified applications also. Next slide. So this is the third I want to talk about, which is about MIMO wireless. So multiple outlet wireless was of course a very important idea. And it came as follows. I was here back in 1986, back in India. I spent 4 or 5 years in India involved with some labs, CDAC, CRL, and so on and so forth. And the Indian Navy, which I was always part of, felt that I should really get back to US. So I started getting calls from naval chief naval staff saying, put in your papers and get back to Stanford. So finally, I did agree to go. I agreed to go back, actually reluctantly. And another person who urged me to get back was Professor Reddy, who's sitting here somewhere. So I went back to Stanford in '91. And next slide. So when I joined there, Stanford said they'll make me a professor, but it's going to take, you got to get, it's a big process, takes a year and a half, and it's a global process of finding a professor. So though I think I had a good chance of getting it, and they would put out a search, I had to wait and go through the process. So I had to find a way of making a living, and I went back actually write a book on ESPRIT. But then there was Professor Gene Golub, who was then a professor, part of the computer science department, but a big name in numerical analysis. Some of you, I'm sure his book, Golub and Van Loon, is very well known. And he used to call himself the SVD capital of the world. SVD is a mathematical tool that all of us use. So Gene had a DARPA contract on the following problem. That is, when you have aircraft, surveillance aircraft fly, I'm sure the Air Force has, our own Air Force has these things, and you want to actually fly away from the enemy zone, but you're trying to pick up signals from what's going on the other side. And it turns out that if you have two transmitters, two radio links running at the same frequency channel, they will normally interfere with each other. But if they're on the ground, the propagation loss is very high. That's how cellular radios work. So if you're about 50 miles apart or 40 miles apart, there's virtually no interference because huge propagation loss. But you're up in the air at 60,000 feet or even higher, the losses are very low. So signals which don't interfere on the ground and therefore can operate, okay, when you try and listen to them, you have a problem because many signals are coming together which are co-channel and it gets garbled. So the way to solve this problem was to use an antenna array and then try and use the differentiation in angular signatures to try and separate them. So this is the problem that Gene Golub was working on, and we never had any real data. So I, had done some labs in India. Certainly, I had done the sonar. So I put together, bought some components and put together a small test jig to actually make some measurements of this system. And we had used cordless phones those days as sources of the co-channel signals. And we built a small equipment with, I think, 4 antennas, not 3 antennas. Next slide. And so what happened was, let's go back. So if these 2 sources were about 20 degrees apart, this is outside Stanford in a building called Durand Building, we were able to separate the signals. When they get closer than that, the underlying matrix conditions become very complicated, become ill-conditioned, and this algorithm will normally fail. And that was expected because we didn't have enough, that was predicted by the algorithm, the mathematics was right and nothing was strange about that. But one day it rained, and it so happened that we did the experiment, but with this box lying was actually inside the foyer of the building. And then by some mistake, or by some what do you call, serendipity, we discovered that even though the sources are next to each other, co-located, we could still separate them. This is completely wrong from the underlying mathematics. So what is going on? Next slide. So it turned out that very quickly it became clear the scattering that was around the building was taking signals which are next to each other, sources, and making them diverse enough at the rate to be separable. And at that time, a little bit of mathematics I knew, information I didn't know very much about it. We kind of knew that the capacity would look something like that. Not exactly that, but something like that. I couldn't actually prove it. But we wrote a patent out, and Professor Kailath was on the patent. And that was the first MIMO patent that came in 1991. Interestingly, Stanford somehow realized that this will be, this was it's a very, Dr. Sarma will know about it, this multiply spectrum. So we have 1 megahertz. This without any cheating, that means it turns out that you can only send more data if you have higher SNR, so there's Shannon theory. But this without any extra power or any extra, just using antennas with no other requirements, actually multiply spectrum. So somebody in Stanford technology licensing thought this will be $1 billion patent. So they invited all the major companies in the world to come to Stanford for a presentation. I did the presentation, and interestingly, everybody walked away. They said it'll never work. And one reason probably was that those days the technology in digital transmission was 4 QAM. Some of you, I know, we need to be communicated to understand what that is. And I claimed, by using this idea, we can go to 1 million QAM or even more. And they said this must be totally crazy. And actually, I was not known in wireless communications at all in the United States. People knew me by ESPRIT, but that was a different community. And I think so they walked away. And I then proposed a project to DARPA, and DARPA said, I had just become a professor, and they rejected, saying this will not work. Okay, next slide. Well, it's now working a lot, so it now underpins a $100 billion industry. Almost every, certainly 3G, HSPA plus, and all 4G, all Wi-Fi, 11N, 11AC. So just semiconductors, we ship probably about $6-7 billion semiconductors, but if we look at all the phones and infrastructure, it's at least $100 billion. And the total number of publications in MIMO today is 14,000 plus, 140,000 plus publications. I think about 12,000 plus patents. And at least 1,000 PhDs, I really cannot count. And that estimate is only, but I myself had 25 PhDs in this group, in my group, in this area. I'm sure Professor Reddy and others have had PhDs in MIMO, and China, out of 1,000 PhDs, at least 600 are in China, certainly a lot in the US and Europe. And so it became an idea which was rejected initially, became actually the cornerstone of a much, much larger system. So it used and every every system in the future will use IDEA because it adds value with very little extra cost and dramatically increases performance. And I remember in that presentation in the 1993, I think, to the companies about 1 million QAM, and they said it's impossible. Today, the 11 AC chips, which I think Broadcom, a company which I work with as an advisor, actually we now have reached 16 million QAM in our transmission. So it'll go to 1 billion QAM soon. So it's incredible. Okay, next slide. The fourth idea is MIMO-OFDMA. So what happened was, so MIMO, we had this patent in 1992. I think it was issued 93. It was rejected immediately by everybody, and I sort of lost interest in it myself, saying that, I knew it will work, but I thought it's too early for the world to accept it. So I started working on some simpler ideas called base station antennas and so on and so forth. So the next slide. So around 1997, I'm not sure Professor Reddy was there at that time, I was doing measurements with antenna arrays. So 1 by 1 is one transmit, 1 receive, 2 by 3, 2 transmit, 3 receive. And I was looking at different things, including interference cancellation and so on and so forth. And I could see in an environment, it looks like a cellular environment, what was signal and interference really bad. I could get enormous separation of those two. This is part of the diversity problem and something else going on here. But I was convinced that MIMO was really real. So 1999, 98 end, I formed a company called ISPAN Wireless to try and build this technology in a commercial way. Next slide. So that was the company in 1988, and because we had to raise almost $100 million of venture capital. And at that time, when I talked about MIMO and MIMO, of course, people were still skeptical whether it will actually work. And even I made a mistake. I was always skeptical of MIMO. One thing was, if you had the signal separability, it would work at some point, but you move your phone by 2 inches, it would not work. So the question was, it wasn't a reliable tool all the time. And what we do today is still not reliable. If it works, we use it. If it doesn't work, we don't use it. So that's how today's systems work. But at that time, I didn't quite get it. So I was always skeptical of spatial multiplexing. But nevertheless, so then we started ISPAN Wireless, and then at that time CDMA was the dominant technology, and Qualcomm was pushing CDMA, and I knew Dr. Viterbi well. I consulted for them earlier, and Dr. Viterbi was very much against OFDMA. In fact, and for some fairly good reason, OFDMA has enormous things like signal diversity and interference diversity, which OFDMA didn't really have at a basic level. But then MIMO would not work with CDMA, and I was trying to convince Qualcomm that it doesn't work well, and it has to use OFDMA, and so that's what we built at ISPAN. And then, of course, you needed a lot of fixes in OFDMA to get the signal and interference diversity. That was easy to do. So ISPAN was the first company actually to build a MIMO-OFDMA based system, and we knew that. So we had a couple of tiny customers, but we already raised a lot of money, and it will take much more money to make it a global standard. Was beyond our means. So then we actually sold the IP to Intel, who then took it and then made it into WiMAX. Next slide. So ISPAN was done around 2000, and then Intel bought the company and then made it into WiMAX, and that happened from about 2003 onwards. In 2004, I actually did another company called Emission to do chips for WiMAX. And then, so WiMAX began to roll forward, and of course was looked at in India also. But WiMAX made a couple of mistakes. One of them was probably due to me. One was Intel dominated the whole picture there, and they felt at that time, this is excusable probably, because phones had tiny screens. They felt that phones will never be internet devices, and will never be broadband kind of devices. We need a new companies, a new spectrum, new kind of a market model for broadband kind of devices. So they didn't make band plans for cellular guys. Cellular people were still sitting in GSM, 200 kilohertz band, 1.25 megahertz bands. They said, forget them. We'll take wide band in the new channel, the 2.5 and the 2.5 and the 2.7 gigahertz, and so on and so forth. That was a big mistake. And of course, when Apple came by and showed one can do some kind of internet on the phone, WiMAX has got into trouble because we had not catered to the cellular operators. Cellular operators then became opposed to it. So WiMAX today is about 50 million subscribers, mainly in US and Japan. India, we gave the spectrum to BSNL, but unfortunately they done nothing with it. It's really tragic. And so then the cellular people, the 2G, 3G, GSM, and the 3G people, they said, we got to move on, do the same thing. They adopted the same technology, WiMAX, and with slight variations. It became called LTE, and LTE 8.9 is now under production, deployed in India by a little bit in Airtel and so on and so forth, but we're still very small. The main deployments are in Europe and the United States and Japan. And the new technology coming called LTE Advanced, where released in 10 and 11, where more things are getting done. And so what started off with IOSPAN has now become the basis of 4G technology. Next slide. So I'll talk a little bit about the lessons that I've learned. So some things, one is of course, you should publish ideas. I actually published only in a conference and got too lazy to publish in journals. For one thing was, if you look at the old equation I had, they had about 6 levels of superscripts in order to define it properly, and that took, those days typewriters, doing that would, I think one page would take one day of typing and cost a lot of money. So I didn't really publish very well with that. And so I think certainly that's one lesson to learn. Second thing is, if you look at ESPRIT came from my understanding, my experience in APSOSONA, where I've been thinking about null forming and so on and so forth. And MIMO certainly came from an experiment. So often inspiration comes from, not from pure theoretical thinking as much as nature and experiments. So you got to, very often you do some measurements, and nature will tell you about interesting ideas. The third thing is, reaction often goes from totally ridiculous to completely obvious. ESPRIT was, of course, different in the sense that people said it's a beautiful idea immediately, but applications have been good, but not to skip. MIMO is a much bigger application, but MIMO was immediately rejected as totally ridiculous. And of course, now of course everybody is completely obvious. And just DARPA, which said no, probably spent tens of billions of dollars building MIMO for military applications. Another thing is persistence in face of repeated failures. I can't claim that I've been a very persistent person, but certainly many areas of innovation to be successful, often you go through lots of failures. And of course, hopefully we learn from the failures, and then we finally succeed. And this is whether it's if you go back to the invention of the first man-powered flight by the Wright brothers, or many or even development of the helicopter, hundreds of prototypes fail, but ultimately they succeed. So persistence is very important, and certainly important in many things, but certainly also for innovation. And it often comes from holding the problem in 1 month for extended period. Certainly ESPRIT, I sort of knew this one there was a determinant goes to 0, and there was some way of doing it, but it must be sitting in my mind for a few months till one day it cracked open. So I think many fundamental mathematical ideas actually come from, you have to hold it in your mind. It actually is solved not by conscious mind, but unconscious mind. And then often newcomers are often source of breakthroughs. And I think it's certainly happened in MIMO. I was completely novel and thing. And even ESPRIT, in some sense, I had not much history in that area, certainly not in building any systems. So I think it helped me to be a newcomer in this area to sort of come up with these ideas. And I'm sure many of you who have done similar things also would notice this thing. So these are some lessons that I've learned, and I think are relevant to idea of innovation. Next slide. So what about the Indian ecosystem, for innovation ecosystem? I think what is green, of course, is very good. Access to global knowledge, and we have as much access to global knowledge as any scientist anywhere in the world. So therefore, we have nothing short of what research in US or Sweden or United Kingdom or Russia has. So very good at that. This is so different. I mean, when I did my PhD, you wanted to get a copy of a paper, it will take 6 months. I beg somebody to send you a copy of the paper. Journals came in late. It is, books were not available. It's very different today. Volume of talent. I mean, I don't think Indians are necessarily any brighter than anybody else, but we have 300, 400 million people who aspire to be, to do well. Some of them want to do engineering, and out of this huge cohort of students, the the very top talent is incredibly talented. So whether I go back to my APSO sonar or my, my offshore R&D in Bangalore, or my interaction with IITs, I'm just amazed at the talent we have in our country. So, and the volume of talent we have is incredible. And we have more, I think, this talent people than any other country in the world. Even, I know China well, I'm a professor there. We have more talent and I mean, knowledgeable talent. So we have enormous ability. And government support for labs, infrastructure, science promotion, I think I think government has done a lot of infrastructure, and you can see it, we see it here in this room, but certainly in Hyderabad and Bangalore, I think government, we can't fault them on that. So when it comes to gray areas, culture, whether we have the right culture for innovation, I think perhaps not, or certainly not completely positive. For example, our universities can't employ foreigners. I can't see why that should be so. In fact, I'm employed by the Chinese, I'm an advisor to them. If they can employ, US, I mean, so China, if you go to China, you find universities are full of, everywhere in the world, people are working with them. But we don't allow that to happen, so it's just, which is not good. So I think we are much more closed than we should be. Teamwork, well, yes, I think we don't have the best marks for teamwork. And the reward systems, certainly rewards within the government there's very little reward system. I'm talking about financial rewards, so that's also can be improved. And also role models. We don't have, I think, too many role models of, United States have people like Wright brothers people have pioneered things in a big way. We don't have so many of them. So we certainly have good scientists, but building stuff which people can use has been limited. And in red, I would put down as areas we have concerns with. I think universities, I think, should be the source of innovation. I think we should do much better. We don't do well in our rankings internationally in terms of publications, new ideas. It's very important to attract bright people. This doesn't come from ordinary people, so we have to attract the brightest people. And so I think we should do more in universities. And industry actually can deliver. If I'm talking about mass market innovation, where billions of people can benefit by that. For example, MIMO does that. That requires industry to deliver that, and we don't have that ability in our country. We haven't built companies which can, deliver innovation. I'm talking about telecom. And finance, risk funding for technology ventures, we don't have. We have, in fact, I keep saying, to build a telecom industry, we have everything. What we don't have is financing and a supportive government policy. I was just chatting with Professor Dr. Sarma here, and he had some ideas. In fact, I'm going to Delhi tonight. I'm going to meet some more people there. But I think this is something can be solved, in fact, and very, very doable. So I think there should be no reason why finance should be a problem. But nevertheless, I think if you look at this scoreboard, we are, I would still say, honestly, we have more going for us than China has. And so there's no reason why we can't catch up or exceed what others have done. Next slide. So one challenge I keep talking about, sometimes even write about, is we import all our mass market high technology. I'm not talking about defense. I don't know what they do, but because I shouldn't be knowing, I'm a US citizen. But you come back to civil jets we fly in, the telecom product we use, computing that we use, precision instrument like MRI, or pharma. Pharma is one area we've done well. We have a very good manufacturing base. But other than that, in other areas we've not done either development or manufacturing, and we should and can do more. And I think the reasons for it is pretty obvious, and I hope many of you here, and certainly I would like to be a part of it, to try and see if something can be done in our country. But also it's important to understand that the government actually has made some statements about indigenous content in telecom, but it's not easy, because we all want to use the latest devices, not because actually the more advanced the device, the cheaper it is. Because that's the problem with technology. The more advanced, the cheaper it is, the more functional it is. So the cost-benefit value is much higher, more advanced. So we want the latest technology. We all have it. We want it. Trouble with high technology is that it's in order to, for example, take wireless chips, Broadcom, Qualcomm, and a few other companies. You got to invest billions of dollars in R&D. You cannot do that till you sell many more billions of dollars of equipment. For that, you got to be global. You got to find markets all over the world. And you have to have, and it turns out you need R&D also all over the world in order to sort of, in order to pick talent everywhere. So unless you're a global company in high tech, you cannot succeed. So in fact, in aerospace, there's only space for two people, the Boeing and EDAS. There's probably no space for third. Chinese are trying to do something, but they openly say that in order for them to be a player, they've got to kill one of these other two companies. So similarly in telecom, there's only space for probably 2 or 3 now. Ericsson, Huawei is there, and ZTE is a smaller shop, and Alcatel-Lucent is also now a weaker company. So essentially, if we want to build a global company, we have to build global. Otherwise, we won't be competitive. We got to, one of these companies will have to die. So it's a tough world with tremendous amount of investments needed. So, and I think we have a lot of things going for it, but we need a government with the necessary will and imagination to make it happen, and it also needs all of us to work together. So with that, let me again congratulate University of Hyderabad for its for the center, and thank you very much.